This video is sponsored by Squarespace. Stay tuned to the end to find out about their special offer for Arvin Ash viewers. How many times have you heard someone describe a difficult concept as, it's not rocket science, meaning it's not as difficult to understand as rocket science is? Rocket science is synonymous with difficult subjects. Wouldn't it be nice to be able to say something like, well, I actually know rocket science, and I think this is more difficult than rocket science. After watching today's video, I think you may very well have the background to be able to say just that, because I'm going to show you how communication satellites work and how they are launched into orbit. Although there are several different types of satellites, these types are the ones that probably have the biggest impact on our daily lives. But to understand what these things do and how they're launched, you're going to have to learn something about, you got it, rocket science. And I'm hoping you'll find it's really not as hard as it's cracked up to be. That's coming up right now. If you've ever used a GPS app to find directions, or if you've looked up the weather for your town or watched a live TV broadcast from a foreign country, you have interacted with a satellite. Satellites affect our daily lives. There are almost 3,000 operational satellites owned by over 100 different countries orbiting the Earth right now, and thousands more are planned for the future. About 550 of these are in what's called geostationary orbits. Communication satellites are typically in such orbits. What this means is that the satellite appears stationary compared to the rotation of the Earth. It stays in the same point in the sky at all times. In other words, you can leave your satellite dish that receives your favorite TV shows in one position and never have to change it. So the question is, how do scientists calculate where to put the satellite so that it remains at the same point in space? Orbital mechanics is rooted in Kepler's laws of planetary motion, published way back in 1609. Newton's laws of universal gravitation, published in the Principia Mathematica around 1687, also plays a role in many calculations. Kepler's laws allow us to calculate the period and speed of such a satellite. Speed is the square root of mu over r, where mu is the standard gravitational parameter, equal to Newton's gravitational constant times the mass of the planet. R is the radius of the satellite from the center of the Earth, and the period has the following formula. Note that the speed and period only depends on the radius of the satellite, not on its mass. A geostationary orbit is circular, and since the altitude of the satellite does not change, its speed must be constant. If you do the calculations, you will find that the geostationary orbit is 35,786 kilometers from the equator. The orbital period is 23.93 hours, or 23 hours and 56 minutes. You might say, why isn't it exactly 24 hours? Well, 23 hours and 56 minutes is actually equal to one sidereal day. This is the time it actually takes for the Earth to complete one rotation with respect to a non-rotating frame of reference. The reason we normally count 24 hours as being one day is because 24 hours is the precise time that the sun is at the same spot in the sky every day. But you have to keep in mind that the Earth moves with respect to the sun. The Earth moves 1/365th of an arc around the sun during this time. That's about 4 minutes. In other words, the Earth has to rotate just a little bit more, about 4 minutes, before the sun is directly overhead. But one full rotation around its axis is actually 4 minutes less than that. Now the question is, how is a communication satellite inserted into an orbit? The first step in this process is to launch the satellite on a rocket that has the payload capacity to carry the satellite to this orbit and can impart the speed necessary to maintain this orbit. In the United States, one workhorse rocket for this task has been the Atlas V. This rocket weighs about 700,000 pounds or 317,000 kilograms at launch and can lift 28,000 pounds or 12,700 kilograms to geostationary orbit. 90% of its weight is fuel, which is typical for rockets. The main engine is powered by liquid oxygen and RP1, which is a highly refined form of kerosene, similar to jet fuel. How does a rocket work? First, a rocket does not rely on the atmosphere to oxidize the fuel like a jet engine does. That's because it carries its own oxidizer. This allows it to be able to function in outer space where there is no atmosphere available. A jet engine would not work here because there's no oxygen available to burn the fuel. Rocket engines are an application of Newton's third law. For every action, there is an equal and opposite reaction. The combustion of fuel causes high-pressure exhaust gases to be expelled at supersonic speeds. The rearward acceleration of this mass of the fuel leaving the rocket nozzle causes an equal and opposite reaction of forward thrust powering the rocket forward or upward during launch. The shape of the nozzle of the rocket is designed to increase the velocity of the exhaust gases further to increase its thrust. Highest thrust is achieved when the mass flow rate of the fuel and exit velocity of the propellant is high according to this equation. The fuel has to be delivered at high volume and pressure to get the thrust required for lift. This pressure is powered by fuel pumps that boost the pressure of the gases before entering the combustion chamber. Because these pumps can boost the pressure, the fuels do not have to be pressurized so high, and the thickness of their storage tanks can be reduced, resulting in weight savings and increased payload capacity. Now you might ask, how are these pumps driven? They're typically driven by using a small amount of fuel to drive a turbine which drives the pump. Now maintaining a stable straight flight is an issue. Early rockets were stabilized by large fins. For stable flight, the center of pressure where the net aerodynamic force acts must be lower than the center of gravity. This is because if its angle of attack changes relative to its flight path, the net force acting below the center of gravity can restore the stability that realigns the nose of the rocket. Modern rockets don't use fins though because of the extra weight and aerodynamic drag that they cause. Stability comes from swiveling the thrust nozzle to keep it stable. This is called gimbaled thrust. A geosynchronous orbit is achieved in stages. Typically, the rocket will take the satellite to its orbital altitude, but the initial orbit is elliptical. This elliptical orbit has to be changed to a circular orbit to become geostationary. So for example, an elliptical orbit may take the satellite to an altitude of 150 kilometers at its lowest point called the perigee, and to the geostationary orbit of 35,786 kilometers at its highest altitude, the apogee. We can use Kepler's laws to calculate the speeds it will have at these points, about 36,500 kilometers per hour at the perigee and 5,800 kilometers per hour at the apogee. The laws of physics are such that the satellite continues on an elliptical orbit until something changes its orbit. This change is done by accelerating the rocket at precisely the right time during its trajectory so that it forms a more and more circular orbit with every pass around the Earth. The thrusters have to be turned on precisely at the apogee to accelerate the craft from 5,800 kilometers per hour to 11,000 kilometers per hour, which is the speed it needs to have to maintain a circular geostationary orbit. As you can probably surmise, there's only one geostationary orbit, and it is at 35,786 kilometers above the Earth's equator. There's no other geostationary orbit, and there are 500 satellites at that altitude. This real estate, even in space, is limited. The total perimeter available is about 265,000 kilometers. This wouldn't be a problem if each of the 500 satellites were placed equal distance apart. There would be 500 kilometers of space between them, but that's not the way the world works. There are many more satellites above the most developed regions of the Earth. They are sometimes less than 10 kilometers apart, and the speed at which they have to move is 11,000 kilometers per hour, or 3 kilometers per second. There's not much space. They're less than 4 seconds apart. The real estate here is a prized commodity, as you might imagine, and is tightly controlled by an organization called the International Telecommunications Union, or ITU, which assigns each satellite a slot at this perimeter. In addition, unless the rocket is launched from somewhere in the equator, it will have an orbit that is not quite geostationary because it will not be in line or in the same place relative to the equator. So for example, when satellites are launched from Cape Canaveral, Florida, which is located at about 28.5 degrees north latitude, the orbit will be inclined 28.5 degrees from the equator. This has to be adjusted, and this requires more fuel. It's beneficial, therefore, for countries to launch their rockets as close to the equator as possible so that less rocket fuel is needed to make this adjustment. In addition, launching from close to the equator gives the rocket added inertia because of the Earth's greater speed of spin near the equator, so that the launched rocket will already be moving at the speed of the Earth's spin at the equator before the launch. Note that not all communication satellites are placed in geostationary orbits. Some are placed in low Earth orbits too. Low Earth orbit satellites can serve the same function, but you have to use many of them as they're moving at such high speeds, and there has to be constant handoff of transmissions from one satellite to another. But the advantage is that these satellites are cheaper to launch and cheaper to make because they don't have to be as powerful, since transmission distances are a lot shorter. So what happens now that we finally have our satellite in orbit around the Earth? We have adjusted to make it a circular geostationary orbit. We have placed it in a correct slot assigned by the ITU, and we have adjusted its angle of orbit so that it is at the same plane as the equator. The first thing that happens is that the solar panels are deployed so that the satellite can have power to function. The main function of the satellite is to receive signals from the Earth, mainly in the form of radio transmissions, amplify them, and then relay them back at a different frequency back to the surface of the Earth. The shift in frequency is used to prevent interference of incoming signals with outgoing signals. Since radio waves are a form of electromagnetic radiation, same as visible light, they do not bend much around the curvature of Earth. Photons are too fast after all. The job of the satellite is to transmit radio waves over long distances. Otherwise, this would require a string of thousands of relay stations on Earth to do the same task. These satellites usually have at least 2 antennas, which may be aimed at 2 different points on the ground. Each is used for both incoming and outgoing transmissions. These antennas are generally made as large as possible for greater sensitivity in receiving signals from Earth, which can become quite faint by the time they reach the satellite. But the size is limited to about 10 feet in diameter or 3 meters due to the space restrictions inside the rocket. Interestingly, a geostationary orbit is sometimes called the Clarke orbit, named after science fiction writer Arthur C. Clarke, who wrote 2001: A Space Odyssey. Believe it or not, he was the first person to detail the usefulness of such an orbit in a story he wrote back in 1945. That tells you that science fiction can sometimes foretell future science fact. The next time you watch satellite TV or use your GPS app, listen to Sirius XM radio or check the weather, think about the rocket science and the incredible technology that goes into allowing us the privilege to enjoy these fantastical technologies. I'm excited to tell you about Squarespace, today's sponsor. Squarespace is a website builder designed to help creators, entrepreneurs, and anyone else looking to have an internet presence create a website regardless of their technical ability. They are known to have the best looking designs and features on the market. You can create a website, blog, or e-commerce store on your own without the need for software knowledge or hiring a developer. If you want to give it a try for free, visit squarespace.com/Arvin Ash, and if you like it, you can even get 10% off your very first purchase by clicking the link in the description below. And if you have a question, post it in the comments below because I try to answer all of them. I will see you in the next video, my friend.